Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are starting a new series of lectures in computer architecture. So today will be the first part of this series of lectures. So what we will be looking at is an overview of what we would study in computer architecture. So the contents for today's lecture would be as follows: is an overview of the computer trends, an overview of the whole course, and we will look at the components of a computer, and we will also look at some things in terms of understanding the performance of a computer. So these are the broad topics that we will try to cover in today's lecture. So what do we mean by the computer revolution? So we say that we are now in a world where computer revolution is taking place. So what do we actually mean by this computer revolution? So essentially it is something which talks about the progress that has taken place in terms of computer technology, and this progress in computer technology has been facilitated by a law called the Moore's law. Now Gordon Moore was a person, he was actually one of the founders of Intel Corporation, and he came up with this prediction that the number of transistors that you have in a processor would double every 18 months. Now remember that the transistors are the basic components with which our gates are constructed and using which the different functional units are constructed. So if your number of transistors doubles, naturally you can have more number of gates and you can have more number of functional units. So if you have more number of functional units, then you can build computers which are more and more powerful. So this is what we have been seeing. So starting from 1960s to 2011 where we are today, you can see that the number of the complexity of the devices has been increasing tremendously, and this has been facilitated by technology improvement. So what has happened because of that is many novel applications have now become feasible. So these are things that you are probably aware of. We now have computers in automobiles, we have computers in cell phones. The Human Genome Project has been facilitated by the development of computers. The World Wide Web, which we are using every day, has been facilitated by computers. Search engines again, which have become a part of our lives, have all been facilitated by the revolution that has taken place with respect to computer technology. And so what we can say is that computers are pervasive today. Everywhere that we go, we are surrounded by computers. We are definitely dealing with computer devices everywhere. So we need to definitely understand what goes into these computers. So that's the basic idea of a course on computer architecture. There are different classes of computers that we see amidst us today. We have the common desktop computers. We are seeing this. You all know that desktop computers are basically general purpose computers, and we run a variety of software programs on them. And in the design of these desktop computers typically is subject to what we call as the cost performance trade-off. Now remember, this term trade-off is a term that we use very commonly in the entire engineering area, and the same thing is true with respect to computer architecture as well. So we always look at what is the performance we can get out of a system at what cost. So we always have to look at this cost performance trade-off. So with respect to desktop computers, we have a wide range of machines available with different cost performance trade-offs. So this is one class of computers that we see. Another class of computers that we deal with are server computers. Now what are these server computers? These are the ones that are providing you major services like the ones which host huge applications for you. For instance, if you look at your railway network system, the railway network system will be running on server which have huge number of computers in them and which are very powerful computers. Okay, so these are typically characterized by what we call as network based systems or clusters of computers, and these are machines which have very high capacity and very high performance, and they are also very reliable. Reliability is also one of the major issues that we look at with respect to these kind of machines. and these typically range from small servers to building sized servers. So if you're looking at large organizations which are providing a huge amount of services, for instance, if you take the Google search engine itself, the Google search engine itself is something which has a host of computers which are interconnected, which are providing these servers. So and these so as we said, we could go from small servers to building sized servers. So this is what we mean by server computers. And then the other end of the spectrum, we have the embedded computers. Server computers are the huge ones, and the embedded computers are those small ones which are hidden as components of systems. You find embedded computers in most of the day-to-day devices that we use. The most common device that we are looking at is the cell phone, as we said. So the cell phone obviously has a computer sitting within it, and that is an embedded computer because it is hidden as one of the components of the system. So you will find we now talk about embedded computers not only in cell phones, in all the other devices that we are looking at today. If you look at your washing machine, if you look at your microwave oven, all the devices that we use today, day-to-day basis, all of them have embedded computers in them. Okay, so they are all hidden components of a system. Now, what is the major issue that we look at when we look at these embedded computer components? It is stringent power and performance and the cost constraints. So if you looked at desktop computers, we said we are looking at cost and performance. You can see that when you look at embedded computers, we look at one more factor, which is the power factor. So we look at power, performance and cost. The reason power is important here is that because these are devices which will be embedded within certain systems. For instance, if you take your mobile phone, you have a processor computer which is sitting within your mobile phone, and your mobile phone itself operates off a battery. So the power that you have to run your mobile phone is limited. So once you have limited power, naturally the components which you have inside that system should obviously consume limited power, which is why power becomes one of the important factors when we look at embedded computers. So this will give you an idea of the different classes of computers that we are dealing with today. As we said, if you look at the proliferation of these different devices, cell phones, PCs, server computers and so on, if you look at how the market has progressed with respect to these devices, you can take a look at this picture which gives you the trend that you have. So you can see that somewhere in 90s, right? If you look at 90s, we had very few number of PCs and TVs. In fact, cell phones were something which was not at all present at that time. Whereas if you look at after 2000, you will find that number of PCs, cell phones, other things have increased quite a bit. So we can see that the processor market has increased considerably, and this entire increase in the processor market has been facilitated by this technological change which has taken place, and we are in the midst of what we call as the computer revolution. Okay. So what we need to do is we need to understand this computer revolution in terms of the device, the basic processor which makes all these things possible. And we also need to understand how this processor is put to use by the users. And when we talk of users, we talk about users as general users as well as the application programmers who develop applications through which these computers can be used. So we need to understand this whole process of how these different things are linked up together and how put together the processor that we design or the process that people have designed are able to give us a good performance or the different types of performance that we are expecting from these various classes of devices. Okay. So overall in this course, if you are looking at what you are going to learn, you can kind of look at it in terms of these 3 or 4 points. So what you will be looking at is how programs are translated into machine language and how the hardware executes them. This is something that we will just have an overview of, because we need to know what is the interface that you have between a user and the system that we have here. And then we will look at what we call as the hardware software interface. That is, you have the hardware which is going to be executing the program and the software which are the instructions which are given to the program. So what is this interface that we have? How is it that in the instructions which are there get interpreted by the hardware? So what does that hardware software interface consist of? Okay, these are some things that we will learn as we go through this course as a whole. While we do this, there are 2 things that we will always keep in mind. One is what determines program performance, because remember that performance is often one of our key points in the entire design. So now we will be looking at computer architecture not just from a user perspective, but the moment we look at computer architecture, we talk about understanding processors from a designer's perspective. So when I design a computer, I am designing it for a particular market and for a certain performance for a certain power requirement and for to be done at a certain cost. So I need to know the factors which influence all these different parameters. So I will be looking most importantly at what are the different things which will determine the program performance and how it can be improved. So this is something that we will learn as we go through this course. Similarly, we will also look at how hardware designers typically have been improving performance, what are the techniques that have been used, and how these techniques have resulted in the various improvements that have taken place. So this is what we would try to do in the course as a whole. So keep in mind that these are the major points, so that we will every now and then refer back to these points and try to understand the entire developments that have taken place over the last 50 to 60 years in the area of computer architecture. So now let us start from writing a program and how this program basically gets translated to something which your hardware is able to understand. Okay. So what is there below the program that you are typically writing? So that is something we need to get a big picture of. Okay. So what do we have here? So we write an application software. So this application software typically is written in some high level language. Now by now I am sure you are all familiar with what we mean by high level languages. Languages like C, right, Java, all these are high level languages. Okay. So high level language, so we all know that we write programs in high level languages. Application software we say is developed in high level languages. Okay. Now then we have other software which is called as system software, which consists of components like compiler, operating system and so on, which will take care of taking this high level code and translating it to something which can be understood by the processor and executed on the processor. So if you look at what these different system software components do, the compiler will be the one that's responsible for translating your high level code into machine code. Now what I mean by machine code is the code that can be understood by the processor. Okay. So high level code is your C or Java language code. So this needs to be translated into machine code. So we normally have a component called the compiler which will take care of doing this. And then similarly we have another component called the operating system, which is basically providing certain services for you. So what do we mean by services? We have different input output devices. So handling these input output devices, managing the memory and storage, all these things are typically handled by the operating system. In addition to that, of course, it will worry about how different tasks can be scheduled on this processor and how all these different resources are shared by the various programs that are running on your system. So all these things are handled by the system software. So then below that we have the hardware, which consists of the processor, memory, IO controllers and so on which your application program will eventually run. So if you look at what we have, the organization of the different components that we just talked about. So below your program you can see, so you have the application software, you have the system software below that, and then we have the hardware which is below that. So the hardware is your central component and your application software is at the outer layer. You have the system software which is sitting in between, which facilitates running of this application software on this hardware. Okay. So this is the overall picture of what we have here. So now let's take a little bit more closer look at what we have, how this translation from this high level language to assembly language takes place, our high level language to machine code takes place. There's an intermediate step there which we call as the assembly language. So let's look at what happens in this sequence. So we have what is called as I said, the high level language, your C or Java like program that we are using, right? And so these high level languages, they give you a level of abstraction which is closer to the problem domain. That is, as a user, I think in some natural language, and I would like to describe my problem in a language which is closer to this natural language. So your C or Java like languages are written in those kind of languages which are kind of closer to our natural language. Okay. So the idea of providing these kind of languages is that it provides for productivity and portability. And below that we have the assembly language, which is a textual representation of instructions. Remember that the hardware basically represents the instructions only in terms of binary digits. This is what we mean by machine code. But between these two, we have something called the assembly language, which again it facilitates our own understanding of what is happening here, which is a textual representation of instructions. So if you look at the entire sequence of operations that take place, you will find that you will have high level program, which is converted by means of a compiler into what are called as assembly language program, and that gets converted by means of an assembler into machine language. So this is the process that will actually take place. We'll take a break now and come back and continue later. Welcome back after the break. So, we were just looking at how a high level language code is converted into machine language code. So, we were looking at the steps for that. So, if you look at the steps, as I said, the high level language program will be given to a compiler, and the compiler will produce what we call as the assembly language code. This assembly language code will go to the assembler and will be taken up by the assembler, and the assembler will work on it and produce the machine language code, which you can see is a series of zeros and ones that we have here. So, these zeros and ones are the ones are what will be actually read by your processor, and they will be executed. Okay. So, this is the overall sequence of things. So, we need to so as a processor designer, we need to look at how these instructions, how these machine language code is interpreted by the processor and how it is able to convert that into some useful work. So, that is what we will try to look at. So, now to understand that, let us look at what are the components that we have in a computer system. So, this is again we are looking at a big picture of what we have. So, you can see that the computer consists of a processor, it has some memory, it has input and output, and there are other issues that we look at with respect to processor, which is evaluating the performance of the processor, and there are other issues like compiler and so on, which are used by the processor in order to make applications possible. Okay. So, this is, so what we need to understand is what happens inside here. Okay. This picture that we have here, you can see, you may not be able to see the details over here, but the details is what we will be looking at in the later part of this course. So, if you look at what are the common components of all kinds of computers. So, we are not looking at a particular type, but we are looking at both desktop, server, embedded, whatever be the type of market, the component computer that we are talking about. There are some components that are common to all these kinds of computers. So, what are these things which are common to all of them? You will find that there will be a processor, and there will be some memory, and there will be input output devices. So, these input output devices will include user interface devices like display, keyboard, mouse and so on. I am sure you are familiar with most of these devices. And then there will be storage devices like hard disk, CD, DVD, flash devices and so on. Then we also have network adapters, because we need to be able to communicate with a network and to be able to communicate through a network with other computers. So, we have network adapters also as input output devices. So, you have in these various types of input output devices, and if you look at, okay, this is just to show you a picture of what a typical system basically looks like. So, you have your monitor here, which is your output device, keyboard here, which is the input device, okay, mouse is also another input device, and there is a network cable which is connecting up the system, okay, that also we know is a input output device. So, let's just take a look at some of these components. We will start with the input output devices, because those are some things that we are more familiar with. So, if you look at a mouse, for instance, look at the anatomy of a mouse. So, we have an optical mouse. So, an optical mouse is something, you can see this picture, this is what an optical mouse will look like. Okay. So, there is an optical device which is used to light up the area and sense the movement that we have here. So, what is happening here, I mean, if you look at what is there inside, these are the components you will see. There is an LED which illuminates the desktop, and there is a small low resolution camera which is also present inside your mouse, and what this does is, it is a basic image processor which will look for a XY movement. So, you are moving in the X direction or Y direction, that is what is captured by the mouse. Okay. Then there are buttons and wheels which allow you to make the movement. Okay. So, this is what you will find as inside a mouse, and this optical mouse is something that we have these days. Earlier we used to have what is called as a roller ball based mechanical mouse. So, the optical mouse has superseded this roller ball based mechanical mouse. So, in fact nowadays we find that the optical mouses are the ones that are more common. So, if you open up the box and see what is there inside the box, that is, we looked at input and output devices. Now, suppose I open up the laptop and look at what is there inside the laptop. So, that is where you are going to find your hard disk, space for your hard disk, memory and so on, right. So, let us look at what is there inside. So, if I open up the box, this is the picture that I will have. Okay. So, there will be a processor sitting somewhere, and typically on top of the processor there will be a fan which is provided for cooling the processor, and there will be a space for a hard disk to be placed over there, and there will be a spot for placing your memory devices, and there will be a spot for keeping the battery, and then there will be place for the DVD drives. Okay. And of course, you will have something called the motherboard, on which most of these different drivers and components will be located. So, you will have all those things somewhere in this area. Okay, so this is what your processor will look like from the inside. In fact, I shouldn't have said what inside a processor. Inside a CPU, that's what you will find. That is, if you open up your computer, this is what a laptop, for instance, that is what you would have found. Now here I am going to show you what it looks like inside a processor. So if you look at this picture here, this picture is giving you what we have inside an AMD Barcelona processor. This is a 4 processor core system. In fact, these days we have what are called as multi-core processors. So which actually consist of multiple small processors sitting inside a single big chip. Okay, so that is what you are going to see here. This is an example of a processor that we look at today, right, in terms of what we are dealing with today. So if you look at this picture, you can see what we have here. This is what that processor will look like. Now obviously we can't make sense of what is actually over here. So this picture on the right side here will give you some details of this. So let me just expand this picture a little bit so that we are able to see this better. So you can see here that we have different cores. This is your core 1, core 2, core 3 and core 4. There are 4 cores here. Okay. So and within each core, if you look at what is there inside a particular core, you will see that there is you have a floating point unit, an FPU or whatever we refer to, and there is a fetch, decode, branch unit, there is an execution, load, store. All these are different things which are going to take place inside the processor. And there is something called a cache, right? There is an L1 cache, there is an L2 cache, some amount of cache basically is some kind of a memory. It's part of the memory system. It's a kind of memory device that you have here. So you have all these different components sitting inside each core. So each of this is a processor in itself, and we have 4 such cores which constitute this entire big processor. That is, you have 4 different processors housed on a single chip. Okay, this is what you have in terms of today's technology. And in fact, now we are talking about not just 4 cores, we are now beginning to talk about many cores. We talk about 8 cores, 16 cores, 32 cores and so on. But what is interesting is many of them inside each core, the basic components that we have are typically similar. So if you understand how a single core works, then we can look at how the multiple cores work and how these multiple cores interact with one another and so on. So we have facilities for all those things which are provided within these kind of processors today. Okay. So that is an overview of a processor as we have it today. If you look at inside the processor, so as I said, so what are the things that we find inside a processor? You will find that there is some kind of a control unit, right, which is going to take different instructions, sequence them and take care of the execution. There is something called a data path that we will find inside. So what does this data path do? It is the one which allows you to perform operations on the data. And then as I said, we saw something called a cache memory, right. So what was this cache memory? I told you that it is some kind of a memory. So what is this some kind of a memory? Essentially it is a small fast SRAM memory which is used for immediate access to data. Now why do I say immediate access to data? You can see that this is placed very close to the processor. We saw that we had these different cache blocks that we talked about over here, right. So we had these cache blocks here, and then I said I have all these load, store, execution units and so on. So we will have data paths which are connecting up these things, and you have this different cache blocks. So this is what we are going to be looking at in more detail. So we looked at the processor. So similarly, let's look at what is, we looked at an input device, right, we saw the mouse, then we looked at what's there inside the processor. Similarly, let's just take a look at what is there, what a hard disk or a storage device looks like. So if you look at where data is typically stored in main memory, what we call as volatile main memory. We call it as volatile because if once power is switched off, you will lose instructions. You will lose whatever data is stored there. So what is stored there could be instruction or it could be data. Okay. So depending on whether you have instructions stored there or data stored there, you will lose whatever has been stored there once you switch off power. So but you have this volatile, we use this main memory as a temporary place from which your instructions and data will be accessed by the processor. So we need to understand that when we talk of data, there are 2 types of memory that we look at. One is the main memory, and then we have what is called as the secondary memory. Basic difference between the main memory and the secondary memory would be that the main memory is a volatile memory. When I say volatile, it means it needs power in order to retain the data, and if you switch off power, it will lose the data. The other is your non-volatile or secondary storage. On the secondary storage, data will be stored more permanently. Even if you switch off power, data will be stored. So what are the different types of non-volatile devices that we have here? We have, these are things you must definitely be already familiar with. We have magnetic disks, then we have flash memory, then you have optical disks, CD-ROM, DVDs, Okay, all these are different non-volatile secondary storage devices that we have today. And if you look at the different memory devices, the devices which are used for the main memory, we use what are called as dynamic RAMs for this purpose. And if you look at the trend that we have with respect to the dynamic RAM, the capacity of the dynamic RAMs has also been increasing. You can see that from somewhere near 16K, we now talk about 1 gigabit and 2 gigabit, 4 gigabit, 8 gigabit kind of DRAMs that we have. So, our primary memory that we talk about, or the volatile memory that we talked about, right, that volatile memory capacity has increased considerably. Okay. And how has this been possible? Again, this has been possible because of the improvement that we have in the electronics technology. Okay. So, we have increased capacity and performance at a reduced cost. Now, these are two very prominent things that we need to remember about memory. Memory, typically what has been happening with respect to memory in terms of technology improvements is that the capacity has been increasing considerably, performance also has considerably been increasing, but the cost has been reducing. So, your performance per rupee or performance per dollar or performance per whatever unit you are measuring cost in has been increasing like anything. So, performance has been increasing and the cost has been decreasing. So, this is something which has definitely helped in terms of building these different types of computer devices that we are talking about. So, if we look at the different overall growth in performance that we have today, just take a look at this picture that we have here. You really don't need to know the details of what is written over here, but all you need to see is that you can see that there is a great improvement here. Now, what is it that I am showing here on the x-axis? X-axis is basically years starting from 1970s to 2011, and on the y-axis we have performance. When we talk of performance, I am talking about how much faster systems today are, these systems are with respect to a processor in say 1978. The VAX 11780 machine which was there at that point of time is taken as a reference, and we are looking at how much faster these different machines are compared to that. And you can see that on the on this y-axis, the numbers that we have here are 10, 100, 1000 and 10,000. It is on a log scale. Okay. So, you can see that by 1986 around 1980s, we had machines which are about 10 times faster. Okay. And about 1990s, we had machines which are 100 times faster. Whereas now in 2000, 2010 and so on, we find that you have machines which are almost 10,000 times faster than the machines that existed at that point of time. Okay. So, this is to give you the feel of how much of improvement of technology has resulted in giving this kind, in giving you so much of power and performance in terms of, in terms of improving the capability of the entire system. So, this is, and whatever I talked about just now is with respect to just a uniprocessor performance. And starting from about 2005 onwards, we have found that the shift has been towards what are called as multiprocessors or multi-core processors. We just saw an example of what a multi-core processor looks like today. The shift from this uniprocessor to multi-core has essentially taken place because of the power limitations. So, we said that for embedded computers we need limited power. So, not only embedded computers, even the larger computers, we find that the processor itself generates so much of heat that it can almost get burnt. So, we need to limit the power consumption of the processor. So, to do that, in fact, multi-core processors have been developed as a solution. So, these multi-core processors are supposed to be providing you better performance, but at reduced power. So, that is the idea that we use here. Okay. So, but we have certain challenges with respect to the multi-core processors as well. Okay. So, these multi-core processors, as we said, they have more than one processor per chip, right. This is something we already saw. But what is challenging here is that it requires explicit parallel programming. That is, in order to get the performance out of these processors, you need to be able to program these processors effectively. So, the traditional or conventional single or sequential programming models that we are used to don't really give you the performance benefit out of these multi-core processors. So, to work with these multi-core processors, now in fact these days there is a lot of emphasis on parallel programming. So, we need to be able to do this parallel programming, which is generally hard to do. Okay. So, because we need now program for performance and take care of how well you are able to balance the load on the different process and so on, and optimize what we call as communication and synchronization issues as well. That is, when you have different processes which are working together, these processes will also have to communicate with each other and synchronize the communication and so on. So, these become new set of issues which have to be faced today. So, if you look at overall the overall development that we have, you can see that from very simple processors which existed at some point of time, we have come up to multi-processors. Okay? And all this development and process has been fueled by the technology improvement, and this technology improvement has given us tremendous improvement in performance. As concluding remarks, I would say that tremendous improvement has taken place in the processing power. As I said, I have been saying this again and again. It's very important because we need to understand computer architecture from this perspective as to how processing power has been improving. And this processing power improvement has been facilitated by means of the technological developments that have taken place. So, underlying technology development is something that we should always understand. And what has also been happening is the cost per performance factor, right? That is, we are getting better cost, better performance at lower cost. So, that is something which has also been improving. And all this is facilitated by means of different layers of abstraction. So, as we saw with respect to software, we saw different levels of abstraction. We talked about high level language, assembly level language and so on, right. So, those are different levels of abstraction which allow us to, or which facilitate developing systems which are able to make use of these improvements that we get in the raw performance which is provided by the technology and by the process which are built on top of that technology. The only limiting factor that we are coming up now is power. How do we get better performance at lower power? So, that is where we are today. Okay. So, so in this course, what we will generally be looking at is how all these different parameters are matched, right? How do we balance between these different parameters? What are the different improvements that have taken place and where we are today? So, that is what we will try to do in this entire course as such. Okay. So, some questions as usual for you to think about. So, I am going to give you one question today, which is this. So, you just take a look at the computer system that you are using, either at your home or at your college or school or wherever, whichever institution you belong to, and you identify the various components which are there in it. Okay. So, when I say identify the various components in it, you should be able to identify what kind of a processor you are using, how much of memory you are using, the different, the complete specifications of your system. So, if you come with that understanding, you will be able to look at how these things are interrelated and how everything works together for the system to give you the kind of performance that you are getting for the various applications. Thank you.